chord so that you can hear that. So why would you use insertion sort over merge sort? Hi, so the HDMI cable for this room is missing. This is an easy fix, but I checked, and it's possible I missed it in this, but I do not see it in here.
Okay. I'll grab you a new one.
Thank you. All right, so that is actually an answer I would accept on an exam. Insertion sort versus merge sort. In merge sort has to take more memory because of the recursive calls. Insertion sort does not use nearly as much memory. It can be done in place. That's a great answer for this one. So there are actually multiple answers to this question. Insertion sort also, it has a quality we call online, which is a very unusual quality for sorting algorithms. Insertion sort, that means that basically you can take a pile of stuff, sort it, and then if I come back to you later and say, oh, I have all this other stuff that needs to be sorted, the work you already didn't go to waste. You can merge in the stuff the new stuff that you're sorting. In other words, you can also just like wait for stuff and sort it as you get it, as it trickles in, which is kind of a useful strategy. Another quality it has is that it is extremely fast when the stuff is almost completely sorted. Like if you have only a couple items out of place, it will sort those extremely quickly. It's a very good sorting algorithm like that. Also, these recursive algorithms often it takes until they get to a higher end, like at least 128 items, to really see a benefit to see n log n being used. So in other words, insertion sort is great if you've got a small size of items you're trying to sort. So it's not particular, so it's memory efficient, it's quick on small sizes, and it has that quality that it's really good on what we call runs. And this is what the current state-of-the-art algorithm TimSort uses. And I say state-of-the-art, it's not really, but it's the standard algorithm, right? And the reason I say this kind of state-of-the-art thing is because you can really, what sorting algorithm you use depends on what context you have. And in terms of general use, TimSort and QuickSort are just about the best there is in terms of general cases. TimSort takes advantage of, it uses merge sort, and merge sort is always n log n, but it also takes advantage of the fact that those runs are, that a lot of data comes in runs, right? A lot of data is sinusoidal, right? So sorting that is often, you've got these nice runs already built into the data, and then sorting them is, so you take those and then you can merge some nice sections. TimSort is a bit more complicated, but that's why it's worth 7 extra credit points if you want to learn it and implement it in your algorithm. So let's see. On Thursday, I will go over something called radix sort, which is an unusual sorting algorithm, but it's worth knowing. It has a runtime of ONW, which is completely different. But that makes it not linear, right? It's not a linear runtime. It is this weird runtime of its own. But again, these sorting algorithms have their use cases. There's a reason I teach selection sort. Selection sort is utter trash. It always, in terms of runtime for comparisons, it always does n-squared comparisons. Always. It always follows the triangular number pattern of O of n versus, sorry, let's go ahead and see this now, because I do actually want to write this for clarification, and it's easier to see, right, on the whiteboard. So, right, O of n, so it's always trash in terms of comparisons, O of n squared, but in terms of the number of times you have to shift items, it's as good as it gets. It's all, a selection sort does O of n swaps. However, comparisons are generally more expensive, that's why we care. But as I use in my example, if we are moving boulders around suddenly, the energy cost of moving might actually be a consideration we want to take. I don't know maybe we're doing Sokuban or something, but I don't know when we'd be moving boulders around, but hey, it's worth keeping that in your back pocket. Now, in terms of so you select your algorithms, you implement them to take the number of comparisons and exchanges. My advice for that is that you've got your sort algorithm, right? However you do it, whatever your sorting algorithm, let's call it XSort because you're going to be implementing this a few times, okay? And you've got let's assume you're doing it over ideally you genericize it, but honestly most of the examples will be of numbers, and that's perfectly fine. And what I recommend is normally for sorting algorithms, this is your entry right over here where you basically say int array and then you don't need anything else. I recommend, to make your life easier, to do this for data collection. You have a data object, which is an object you will have to make, but honestly it's not a very hard one. Because what you're trying to do is you're supposed to, let's call it instead data. What you're trying to do, right, is that you are currently trying to compare the number of comparison. You're keeping track of the number of comparisons and exchanges for a particular run on an array, right? Okay, so you're doing that. And rather than trying to return multiple values, like return the number of comparisons, return the number of exchanges, or keep something out of, or try to have a bunch of static variables that you're trying to keep track of, you can create a data object, a new data object, and pass it into your sorting function. And the data object is very simple. Data will just simply have a int comp and int exchange. It's literally just a tuple of datas. It's just literally a tuple that counts the number of comparisons and exchanges. And so when you do a comparison, you can just simply say data.comp++, and when you do an exchange, you can say data.exchanges++. And then you don't have to worry about even having to return it because it's the same data object. Also, this helps with your recursive functions because you just simply pass this into your recursive functions, and it's the same object in all branches of the recursion. There you go. Third thing, and this is the one that the students mess up most. I mentioned about testing on data that is sizes of power of 2. That what I'm referring to is that you're going to be testing on arrays of random numbers like 12, -2, 15, right? Something like that. But the length of this, right? The length of this is some 2 to the x, right? It's some power of 2. Or you could do powers of 10 or whatever. But I need some data. So maybe you test it on something of power 2, that's maybe you test on basically 32, then 64, then 128. That way, when you graph your data, I can see something like this, where you have your exchanges, maybe. I mean, I care about comparisons, but I wrote exchanges. Doesn't really matter. But basically, you've got 32, right? Then you've got 64. Then you've got 128 for your data points, right? And so you're obviously not going to have a line, but you can, or a curve, but you can have these graphed points, right? That I can visually see and extrapolate that there's a line there. Make sense? Because if you just simply do a bunch of points like this, you do a bunch of tests on something of size 10, they're all going to look the same. You'll also notice that your run times, sometimes are weird. Sometimes if you check a run, because they tell you to keep track of run times. Run times are sometimes weird. If you do a runtime, you might do something on size 10, and it takes 0 milliseconds, okay? Because it didn't even register to round up. And then you test it on size 20, and it's 1 millisecond. And then you test it on size 30, and it back down to 0 milliseconds. How did that go slower? And the answer is scheduling sometimes is weird. You're getting to right now the sizes are so small that the operations that the computer just does in the meantime, such as updating the screen and stuff like that, are kind of getting in the way of processing. That's an example, but it's like computer scheduling is a very complicated kind of problem. And right now the overhead of having to do the additional work for sorting is so low that all the other stuff is just gonna interfere with your tracking the amount of time. So I didn't want to take that for too long, but again, just this will help you collect your data. I recommend creating for each of the functions you do a list of data objects so that you can just easily add them and just get as many samples as you can. The entire point of this is to teach you that basically there's an easy way that sometimes you're going to need to collect data, and you'll have a much easier time collecting data if you can just run the program and it dumps all the data out into a file for you, rather than trying to go through a bunch of print statements and grab them. It's always because you can just dump it out into a pre-made CSV file and then automatically open that in Excel, and it's nice that it's automatically done. Also, if you prefer to work in Python, I don't care if you don't have to do this in Excel. You can use it in Matplotlib, and of course by Excel I mean you can also use Google Sheets. I don't really care. I just want graphs. All right,